Hello everyone, welcome to Marketing Research. This is chapter 18, Marketing MKTG 457, Marketing Research. In chapter 18, let's talk about some advanced topics in linear analytics. Okay, advanced topics in linear analytics. After this chapter, you should be able to have a better understanding of the meaning of covariance and correlation theoretically. Okay? Computer covariance and correlation matrix, separate causal relationship from other types of relationship to build explanations, and use multiple regression for predictive purposes, and appreciate the arithmetics of ordinary least square, or OLS. Excuse me. All right, understanding covariance and correlation. Right? Sometimes we want to find the relationship between two variables, right, or also associations, right? And the measures of association capture how much one variable changes as another variable changes. Okay, so measure of association captures how much one variable changes as another variable changes. So we want to find the relationship between the two. Okay? Covariance. Covariance is the absolute amount of association between two variables determined by how a change in one variable corresponds systematically to a change in another. That's called covariance. Okay, is the absolute amount of association between two variables determined by how a change in one variable corresponds systematically to a change in another. Right. So we have covariance here, right, between x and y equals to xi minus x bar times yi minus y bar, multiplication of the product of that, added up from 1 to n and divided by n minus 1. Okay, and that's covariance, right? And or that's for the sample, and for population we use xi minus mu x and by y and the mu y, the same way. Right. Keep in mind here, for sample the degree of freedom is n minus 1. For population the degree of freedom is n. Okay, it's n. Okay. That's covariance, or COV, covariance of that. Okay, this is the formula, right? Population and sample. Okay, correlation on the other hand, or correlation coefficient, is a statistical measure of association between two variables expressed on the range of -1 to +1. A -1 to +1. The covariance could take many numbers. The correlation though, correlation can only take a number between -1 to +1. Okay, a standardized representation of covariance. Okay, covariance, standardized, representation is correlation, which is more useful. Okay. If the value r equals +1, r correlation coefficient, we use a little r to denote that. Right? If r is +1, equals +1, we say there is a perfect positive relationship between the two. A perfect positive relationship exists if r is +1. If the value of r equals -1, we say there is a perfect negative relationship exists. Okay? And if the value equals 0, there's no relationship exists. Okay? No relationship exists. Okay? A correlation coefficient indicates both the magnitude and the direction of the relationship. The closer to +1 or -1, the magnitude, the degree of association is higher, right? The closer the value is to 0, the smaller the magnitude of correlation. And the direction, of course, is a positive. Is a positive number is larger than 0. We say the positive relationship. Then if it approaches plus 1, 1.0, right, is a perfect positive. If the R is negative number, is less than 0, we say there is a negative relationship. When it reaches minus 1.0, it's a perfect negative relationship. Okay? So this is how R is calculated. The correlation coefficient between two variables. Okay? Looks complicated, but it's not. Actually, it's quite simple. Right? It's xi, each x value, minus mean, x bar, times yi minus y bar. The product of the two is summed up from the first observation, to the last one, to the nth one. And then here, xi minus x bar squared summed, y minus y bar squared summed. The product of two, we take the square root of that, right? So keep in mind, rxy equals ryx. So the correlation between two variables, doesn't matter which one is first, which one is second, right? They're the same, okay? And basically, this part here is sigma xy, okay? Covariance of xy, and here is the sigma x squared and sigma y squared, okay? So the sigma x squared, this one here, is overall variance of x, and this is overall variance of y. And this one, sigma xy, is overall covariance of x and y. Okay, you can see this is the correlation coefficient. The standardized measure is basically the ratio of the covariance. Okay, this is a formula. Okay, x and y values are plotted on one another, and in the Cartesian plane is called the scatter plot. You can do a scatter plot. In this scatter plot, you can see in this case r is 0.30. So it's a positive relationship, right? Positive relationship, but it's not very strong. It's only 0.3. Okay, and this one is positive, but r equals 0.8. So that's a higher, stronger correlation, right? We call it high positive correlation. This would be a low positive correlation. Low positive, high positive, okay? And if it's 1.0, it's a perfect positive, meaning that all the dots are on the line, okay? Here you can see the trend, you see the line, right? Here you can see the trend, but not clearly forming a line, okay? These are all in the case of R being positive. When R is negative, when R is 0, there's no correlation, right? You can see it's scattered all along here, and not pointing to any direction or any trend line here. But this will be similar to that one, right? It's negative. I'm sorry, not exactly the same as this one, but it's a negative, right? It's a moderate negative correlation. It's 0.6. Between about 0.6 and 3.8 is 0.6, but it's minus, it's negative. So meaning that when x goes up, y goes down. Okay, that's why it's a negative. Minus 0.6. So there's a moderate negative correlation. And then with r equals minus 1.0, it's a perfect negative correlation. Okay, perfect negative correlation. Correlation calculation, we can illustrate correlation calculation, okay? Consider an investigation made to determine whether the average number of hours worked in manufacturing industries relates to unemployment. We can look at that, right? And the average number of hours worked in manufacturing industries relate to, its unemployment. The two variables here, right? The correlation analysis of the data is carried out on exhibit 18.4. Okay. Notice that the exhibit breaks down the different components needed to compute variance as well as covariance and correlation. The correlation between the two variables, hours worked and unemployment, is minus 0.635. That indicates there is a negative relationship. It's pretty strong, right? Pretty strong negative relationship. Negative meaning the more the hours worked, the less the employment. So when the number of hours goes up, unemployment goes down. Okay, that makes sense, right? Here's an example here showing the unemployment rate, right? The unemployment rate 5.45, 4.4 is that true, etc. The high is 6.7 and 6.8, I believe. The lowest is 3.5. Okay, the number of hours worked, around 40, more or less. Okay, and that's the xi minus x bar. How do you calculate that? Right, you calculate the x bar by averaging all this unemployment rate. Okay, and then the xi, the average here is more 5.5 minus that x bar give you 0.51. Okay, and then this column you get xi minus x bar squared. You just square this column here, and then you do the same thing for the yi minus y bar squared, and then you multiply the two. Okay, you multiply the two. You can multiply this 0.51 and minus 0.71 to get minus 3621. Okay, that's the calculation. Okay. There's another term called the coefficient of determination. Okay, remember there's a difference here, right? There's a covariance, there's a correlation, there's a coefficient of determination. If we wish to know the proportion of variance in y that overlaps x, or vice versa, we can calculate the coefficient of determination by squaring the correlation coefficient. Basically, coefficient of determination is a correlation coefficient squared. Okay, squared. Okay, so R to R equals, right, xr squared, right? And this one squared. Okay, that's coefficient of determination. Okay, what's the meaning of coefficient of determination? The coefficient of determination represents a measure of association between a dependent variable and an independent variable employed to predict it. In other words, to what degree, what percentage, how much of the variance in that is explained by your model. That's R squared. Okay. Covariance and correlation matrix. A covariance matrix contains the covariance for every pair of variables among a set of metric variables, with the off-diagonal elements displaying covariances and diagonal elements displaying variance. Okay? The covariance matrix, often abbreviated with the bold capital S, is a square matrix summarizing all the relationship among variables that retains the absolute scale value. Okay, S, right? S captures both the common scalar covariance and variance and the level. Higher value represent the larger numbers of the set of variables. Okay. Covariance and correlation matrix. A correlation matrix is a standardized covariance matrix, where it retains all the information about relationships in the off-diagonal elements, the actual correlations. The information about the level of variables is removed as all the variance becomes standardized to 1. So every diagonal element is 1. Okay. One way to produce the correlation matrix is to first standardize all variables yielding z-scores. Remember z-score, we call it z-scores that express variable values in standard deviations away from the mean, and then compute all possible covariances. Okay? Researchers often compute correlation matrix early on as they provide a quick summary of how variables, corresponding to each other, vary corresponding with each other. Okay, that's a good idea to do that. Okay. Now let's talk about the causality and explanation. Causality and explanation. There are three conditions necessary for causal conclusion. Okay, and we talked about this before. Let's reinforce that here. Okay, the three conditions necessary for causal conclusion: temporal sequence, concomitant variance, and non-spurious association. Temporal sequence, the cause must take place before the effect. Okay? For causality to take place. Concomitant variance, meaning the two must change together. If one changes, the other changes. Okay? And non-spurious association, we know that's the hardest to establish. That means that there are no other, possible explanations exist. Right? Then you can make your conclusion. So, in regression analysis, we provide evidence of concomitant variance in the form of significant parameter coefficients. We can use regression to provide evidence of concomitant variance. Temporal sequence, you know that when you collect the data, right? You know the data, nature of data. So if we can provide, evidence for concomitant variance, we can establish, we can use regression to establish causality. Okay? And the non-spurious association, we just do the best we can. Right? It's not possible to exclude all possible reasons or causes. Right? So the issue of temporal sequence must be sorted out logically. Okay, temporal sequence, you sort it out logically, then you'll be okay. Control variables, right? What's control variables? That there are variables that are not involved in any causal assertion or hypothesis, but are measured and included in an effort to understand the true effect of hypothesized variables on dependent variables. We call those control variables. Variables that are not involved in any causal assertion or hypothesis, but are measured and included in an effort to understand the true effect of hypothesized variables on dependent variables. Okay? The oval shown in the next exhibit represents the variance of the independent variable x, the dependent variable y, and the control variable c. Okay? It also illustrates the notion of multicollinearity, which occurs when multiple predictor variables including the regression analysis, correlate with each other. Okay? How much correlation or shared variance among independent variables is large? Okay? The variance inflation factor of VIF represents an overall estimate of the variance overlap among the independent variables. Right? How much overlap is too much? In typical marketing research, VIF of 5 or more is a clear indication of problems with multicollinearity. Okay? Multicollinearity. Okay? When the VIFs are between 2 and 5, the analyst becomes cautious and looks for signs that indicate the results are suspicious. The adjust R squared takes into account multiple dependent variables overlapping. Okay, in that exhibit. Hold on one second. Another term here in this is called the residues. Right? What is residue? A residue means the portion left over or unexplained after the predictor variables are included in a model intended to represent y. Okay, you have a model. Okay, you have your variables included in the model to predict the dependent variable. Okay, and then there's the remaining portion. That's the variance that is not explained. It's called it's a residues, right? Residues. The residues. That's what residue means. Okay. So major assumption of any generalized linear model, including linear regression, is that the residue terms are independent. You know, we assume that the residue terms are independent. Okay. The most regression program provides an easy mechanism to plot residues. Because residues you can plot it to see if it's significant or not. Okay. When residue plots reveal a random distribution of dots, the researcher can conclude that the error is white noise. There's white noise, and then it's not a problem. Underspecification means a model does not include a complete set of variables that would be necessary to offer a complete explanation of the dependent variable. Underspecification means a model does not include a complete set of variables. You didn't have a good model, perfect model. Okay. Residues, exhibit 18.7 contrast plots of systematic versus random residues, right? In the frame on the left, the plot of residues against the independent variable x displays a random pattern with no easily detectable difference in the size of residues for any value of x. The right frame depicts larger values in absolute value of residues for smaller values for larger values of x, and smaller values residues for x values close to the scale midpoint 4. The left frame of no pattern depicts a state known as homoscedasticity, while the right displays the state known as heteroscedasticity, where residues, change values over some variables. Okay. There's homoscedasticity versus heteroscedasticity. Homoscedasticity and heteroscedasticity. Okay. The steps in regression aim at explanation. When you do a regression aimed at explaining something, right, you select the appropriate dependent variable and independent variable based on the research questions or the hypothesis derived from them. You know, in your project, I want you to use your attitude measurement, opinion attitude measurement using Likert scale as a dependent variable. And you can select some independent variables. Okay, independent variable could be like demographics and other things. Okay, based on your research question, you can select any relevant control variable available in the data and set and include as additional independent variable. Okay, you can perform multiple regression with the appropriate software. Okay. And then you interpret over the overall model F and R squared. And if the model is statistically and practically significant, then you can move to step 5, which examine the VIF for potential multicollinearity. If no concerns emerge, then you can proceed. Okay, you can interpret individual parameter estimates. Consider statistical significance of each variable. The valence of the relationship is a positive or negative, and the relative size of the relationship is best captured with standardized regression coefficients. Okay? Then you examine the residue plots. If no patterns emerge and the homoscedasticity is evident, the researcher can confidently interpret the resulting parameter coefficient for explanatory meaning. Okay? Regression for prediction. Remember, not all regressions are intended to explain some dependent variable. And from time to time, the researcher's concern is merely prediction. Okay? Merely prediction. In other words, the question involves forecasting what y might be more than y comes to take on that value. Okay? We just want to know the scale, the magnitude, not the reason behind. Okay? In these cases, the researcher charges. The researcher can charge the analyst with generating an accurate prediction of y for any value of x as a priority over explanatory interpretation of beta. Okay? Basically, you're interested in predicting that, not explaining that. Okay? So predicted values y are represented as y hat. We call the y hat predicted value of y. Okay? One way to determine the relationship between x and y is to simply visually draw the best fit straight line through the points in the figure. Okay? That is, try to draw a line that goes through the center of the plot of points. Okay? For any given value of the independent variable, a prediction can be made by selecting the independent variable that goes along with the value. Okay? In this case here, the best fit line of knocking out pins, right? This is the beta b0, the y-intercept, right? This is the b1, the slope, the raw parameter, slope coefficient. This is the actual y for dealer 3, okay? Y hat for dealer 3, that's predict one for dealer 3, and the y for dealer 7, actual, this is actually predicted, and then actual for dealer 7. You can see that this is a line that represents the dots here. Okay. Errors in prediction. We would like to an estimation technique that will place our lines so that the total sum of errors over all observation is minimized. Okay, we want that line. Okay, in other words, one in which no lines fits better than your one. Okay? Although with good guesswork, visual estimation may prove somewhat accurate. Okay? Perhaps there is more certain method. Okay? Also, time series analysis. With time series analysis, generally time series models place an emphasis on prediction over explanation. Again, prediction over explanation. The goal is to forecast some dependent variable for a future time period. Right? You extrapolate. Okay? In terms of the explanatory power, a problem with time series analysis is called autocorrelation. What is called autocorrelation? Autocorrelation refers to the fact that observations from different time periods are almost always correlated with each other. Always each other. Thus, the residues are unlikely to be independent of each other without corrective measures. Okay? One simple corrective measure involves including number of count as time period. Okay? Ordinary least square illustrated. Let's illustrate that. What is ordinary least square? Is a relatively straightforward mathematical technique that guarantees that the resulting straight line will produce the least possible total error in using x to predict y. Okay? That's the ordinary least square. In using squared division, ordinary square uses squared deviations. The sum of squared errors, or SSE, is all the errors added up. Okay? EI here is yi minus y hat I. So that's the residue, right? The difference between the actual observed value and estimated value of dependent variable in the observation, right? Yi is actual observed value of dependent variable. Y hat is estimated, and is number of observations. I is the number of particular observation. Okay, that's and then this is the regression equation parameter estimate. This is the regression equation. Y B1, B0 that's intercept, B1 the slope, x1 and plus the error. B1 is calculated by that. Okay, xi my yi summed up times n, summed up x, summed up y, multiplied, then the squared sum, then squared, and the sum squared, okay, to calculate your B1. That's your slope. B0 is simply, y hat, y average, y bar minus B1 times x bar, okay, to calculate your intercept, okay. This regression equation, this parameter estimates, okay. Statistic significance, okay. Basically, the equation is using a f-test for regression, okay. F is mean square regression divided by mean square error, okay. And that's mean square regression, mean square error, and you calculate the R square, which is SSR or SST, sum of square regression divided sum of square total. That's how we calculate that. Okay. I think remember also what R square represents. That's a determination of coefficient, right? That is how much of variation is explained by your model. Okay. I think that's all I have for this chapter. Okay. Thank you very much. I'll see you next time. Okay. Because good and bad values of coefficient determination depend on so many factors that no precise guideline is appropriate. Okay. So the proportion value explained by R squared. Okay. Okay. See you guys. Thank you.